In this section, we start the basics of probability. So let me do some examples to show you what we're getting at. I'm going to flip a coin one time. What's the probability of getting heads? So I can write that in the following way. The probability of getting heads is, well, let's take a look at what we have here. If you flip a coin one time, the total listing of outcomes is either heads or tails. Heads is one out of two outcomes, and we agree that these two outcomes are equally likely to happen. So whenever we're talking about rolling dice, pulling cards from a deck, or coins, we're always talking about fair coins. So there's always a 50-50 shot of landing on either heads or tails. So one way we could write the probability of getting a heads is we could say that it's 50%. Or, if we wanted to, this might even be better, 1 out of 2. Try the same thing with rolling a coin or flipping a coin twice. So let's try that. So now, if we take a look, I'm going to do 2 flips. I'm going to do 1 flip. The first flip, if you will, can be either heads or tails. So there's our first flip. Then the second flip, I could get a heads again, or I could get a tails, as it does not know what it got before the second toss. So now what you do is this. Follow along this branch here, and this branch says I had heads followed by another heads. So I'll put H and H. And then if I follow along this other branch, I first hit heads and then tails. Next, if I look at the other flip from the beginning, the one that yielded a tail originally, once that tail is established, when I flip the coin again, I can either get a heads or a tail equally likely as before. So now if we follow along this branch here, we have tails, heads. And then finally, the very last branch is tails, tails. So what you see here are a collection of 4 outcomes. Let's flip a coin 3 times. So I'll do exactly what I did before. I have my start. My first flip can be either heads or tails. So there's my first flip. Then I can continue on and get another heads, or I could have gotten a tails. And then from this tails down here, I could have gotten a heads or a tails. Now, that was the second flip. On the third flip, each of these 4 outcomes has 2 possible places where they can go. I can, once again, go H or T. Now let's follow the branch. So if I start here at the beginning, I have H, H, H. So this is 3 heads when you flip the 3 coins, or flip the coin 3 times. And if I go along this, I have H, H, T. Now let me go and continue this branch here. That will break off into an H and a T just like the other ones. And so along this branch then I have H, T, H. And then I have H, T, T. And then down here I'll go ahead and break these off. So then that can get another H and another T. So if I follow this branch, I have T, H, H. and then I have THT, and then finally this last one, I can have either an H or a T. And so following along here, I have TTH, and then we have TTT. So notice there's a total of 8 outcomes, and I'll let you in on a little secret here. For the first one, there was 2 outcomes. That was 2 raised to the first power. For the next one, we flipped a coin twice, we had 4 outcomes. That's 2 raised to the second power. For 3 times, we have 2 raised to the third power. Flip a coin 4 times. And there are 2 to the 4th outcomes. That happens to be 16. That's handy to have in mind. This is part of what we call the multiplication principle. Let me go to another idea. Toss 2 dice. So let me start with first tossing 1 die. What are our outcomes? Let's see, we have 1, 2, 3, 4, 5, or 6. On the other hand, what if we toss 2 dice? And when I say die or dice without any more explanation, I'm speaking of one that has 6 sides. There are some examples that we do where the dice have more than 6 sides, but we'll be sure to tell you that. So whenever we don't make any description of the die or dice, it's 6-sided. So we have 6 outcomes there. So now let's take a look at toss 2 dice. On the first die, we have 6 possible outcomes. And on the second die, we also have 6 possible outcomes. But combined, how many outcomes do we have altogether? And I'll show you how we can do it. Let's take a look at the first die. All right, let's say we get a 1. Then the second die can be any of 1, 2, 3, 4, 5, 6. There's 6 possible outcomes when the first die is just a 1. So if I keep track of the outcomes over here, there's 6 of them. Well, if the first die is instead of 2, well, I still have exactly the same 6 outcomes possible in that case as well. So there's another 6 outcomes. The next die is a 3. You can do this for all of them. No matter what you roll on the first die, the other one still has all 6 possibilities available to it. So let me keep track of all these. Here's 6, here's 6 more. Then we have 1, 2, 3, 4, 5, 6. There's another 6. And then finally 1, 2, 3, 4, 5, 6. 6. If I add up all these possible outcomes, you'll find that there are 36. But better than that is the following. 36 equals 6 times 6. So up here, when I was filling out these blank spots, the first die had any of 6 possibilities available to it, and so did the second die. And what you do with these numbers is you multiply them. So there's a total of 36 outcomes. Or another way to look at it, if you want, is 6 raised to the second power. Toss 3 dice. Then we're going to have 6 to the third, which equals 216 possible outcomes, I should say that. So basically, the counting principle works this way. We look at the number of ways we can do one task, and then we look at the number of ways we can do a second task, and we multiply them together, so long as the tasks are what they call independent of each other. So let me go ahead and write down what we call the multiplication principle. Here, let's have two tasks. If task 1 has m outcomes and task 2 has n outcomes, so whatever m and n are, they're numbers, they're whole numbers. So if we have task 1 has m outcomes, task 2 has n outcomes, then the combined task 1 followed by task 2, so then the combined task task 1 plus task 2 has n times, well, I should put them over here, m times m, so m times n outcomes. So in the case of the die, if we were tossing 2 dice, there were 6 outcomes for the first die, and there were 6 outcomes for the second die, so you multiply them together. You get 6 times 6 is the same as 6 squared. As an example, suppose you have five shirts. So suppose you have 5 shirts, 3 pairs of shoes, and 4 pairs of pants. How many combined outfits can you create? So we can simply look at it this way. I could look at how many shirts I have available to me, and that's a total of 5 of them. So there's 5 ways to choose a shirt. That's like my first task. Then shoes, there's 3 pairs of those. And then finally, what's the last thing? Pants. There's 4 pairs of those. All we do is multiply these all together. And it looks like we have 15 times 4, which is 60 outcomes. Well, instead of outcomes, let's call it outfits. You dine at a restaurant that has 4 courses. Let's see, we have a salad. We've got soup, an entree, and then dessert. And let's say if you look at the salads, we have 5 to choose from. And then soup, suppose we have 3 to choose. And then the entree, suppose there are 10 entrees available to you. And then finally, dessert, let's say there's 6 to choose from. How many 4-course dinners are possible here? I probably should say how many different 4-course meals are there here? So we simply do like I did before. I'm going to look at the number of salads, which I have 5 of them to pick from. Then we have soup, which is 3 to pick from. Then we have an entree. There's 10 of those. And then finally we have 6 of the desserts to choose from. So we're simply going to multiply all these together. 15 times 60, I believe, is 900. So 900 possible meals are at this particular restaurant. A 10-sided die is tossed twice. So we can look at it this way. Toss one, and then the second toss. 10 possibilities for each toss. So we have a total of 100 possible outcomes. And I misspeaking here. This is always possible. This lists all the ones that you can possibly have. Now, what if we were to toss it 3 times? Well, here you're going to fill in exactly like you did in the previous problem, except you're going to have to do a third spot for the third toss. And so what you're going to end up getting then is 10 times 10 times 10, which is 10 to the third power, or 1,000 outcomes. How many ways are there to select 3 cards in order, one after another, from a deck of 52 cards. So 3 cards, we could look at it as selecting a card, card 1, and selecting a second card, and then selecting a third card. So if we look at it that way, we have card 1. When you select the first card, you have 52 cards with which you can select. Then you go to card 2. After card 1 has been selected, there's only 51 cards left. So I'm going to get 51 here. And then finally, card 3. After 2 cards have already been drawn, there's only 50 left for card 3. 52 times 51 times 50 equals 132,600. How many ways are there to line up 5 suspects for a police lineup? Well, and this is the same thing. You're going to have your people broken down. The first one, the second one, the third one, the fourth one, and the 5th one. So if you look at the very first one here, you have 5 suspects to choose from, so one of them is placed. That means there's only 4 left. So the next one, you only have 4 to choose from, and then you can see after that it goes down. And so if you multiply all those things together, you're going to see that there's a total of 120 ways to do this. Note, try to find this symbol on your calculator. There is a notation for when you take 5 times 4 times 3 times 2 times 1. They call it 5 factorial. This is whenever you take a whole number and you multiply down like this until you get to 1. That's factorial. See if you can find, factorial will appear in our work. See if you can find it in your scientific calculator, if you can find out where it is. Anyways, that is, of course, equal to 120. Let's look at some basic examples of probabilities. Let's start with really simple ones. So let's flip a coin one time. All right, the outcomes that we can get are very simple. We can have either heads or tails. They're equally likely. So when you flip a coin once, what's the probability of getting a head? So the notation I'll use is this. So this is the probability of getting H. So P with H in parentheses, the probability of getting heads is 1 out of 2. Since heads represents only one outcome out of a total of 2 outcomes. Let's continue this. Let's flip a coin twice. And before I finish that part of it, you should make note too that the probability of getting tails is also 1/2. Whatever I say about heads, tails has the same information available to it. Now let's flip a coin twice. Let's take a look at our outcomes. Here, we could have had 2 heads, heads, tails, tails, heads, or tails, tails. So there's 4 possible outcomes. Let's take a look at some questions that you could have. What's the probability of not having any heads? Well, if we look through here, there is only one situation that has no heads. That's 2 tails. So we only have one situation out of the total of 4 of them. How about I go the probability of 1 head? So in all of my outcomes, let me find where there's only 1 head. So we have heads, heads, no. Tails, tails, no. But these 2 right here in the middle, they both only have 1 head attached to them. So there's 2 of those out of a total of 4. And then finally, the probability of 2 heads is we have 1. We only have 1 of those out of a total of 4. So what you've done here is you've exhausted all the possibilities that can happen here. If you notice, 1/4 plus 2/4 plus 1/4 adds up to 1. So that means that it's covering 100% of the data. Now, let's flip a coin 3 times. To help you remember how the counting goes, I'm going to do it again. So we're going to start over here. And on my first flip, I got either heads or tails. I'll continue then. On my next flip, I can get heads. I think I'm going to make that. I could get heads or tails again. And on the third flip, once again, I could get head. Let me put it in a different spot than that. Put it over here. Heads, tails. So let's follow along here. We have heads, heads, heads. The next one after that was heads, heads, tails. This one here, branch off. We have heads, tails again. So the next one I have is HTH and then HTT. Finally, this one, I don't know what happened here. Let's get a second flip on this thing. H or T. and then a third flip on it. H or T, and down here the same thing. H or T. And once again, I don't want to bother, I want to pull these inside so that they don't interfere with my labels here at the ends. All right, so for this one here, we have THH. The next one we have THT. Then we have TTH. And then finally TTT. So we can play the same game we did before. Notice that there's 8 outcomes. 8 is equal to 2 raised to the 3rd power. You flip the coin 3 times. Now if I take a look, what's the probability of no heads? Well, if I scan all of these outcomes here, there's only one situation out of the 8 that has no heads. That's all tails. So that's 1 out of 8. How about the probability of having exactly 1 heads? So if I scan through these, I got 3 heads, 2, 2. There's 1 head, so I have 1. There's 2, and there's 3 of them. So I have 3 out of 8. The probability of 2H, how many of these have 2 heads? I have 1, 2, 3. So 3 out of 8 also. And finally, the probability of having 3 heads, there's only one situation where that occurs, and that's 1 out of 8. One thing you can do to check yourself to make sure you've exhausted all the possibilities is take these numbers and add them up. If you'll remember, when you add up the fractions, so long as they had the same denominators, all you had to do was add up the numerators. So I'll do that. 1 plus 3 is 4, plus 3 is 7, plus 1 more is 8. So if you add these up, it turns out that it covers 100% of the data. Definition: any collection of outcomes is called an event. If A is any event, then the probability of that happening, so the probability of A occurring, equals the total number of ways A can occur. We're going to divide that by the total number of possible outcomes. Here's an example out of your textbook. These methods that we're using that are using known probabilities, like the probability of a coin equaling 1/2, or the probability of getting a number when you roll a die equals 1/6, they're what you call theoretical probabilities. And the methods we're using here, since they're strictly computational and they're not based on research or gathering data, these are all referred to as theoretical. Anything that we do where we gather data, you might call it applied. So let's start with, look at these examples here. We want to find the probability of the following events. So we want to look at exactly 1 head when you toss 2 coins. So let's take a look at A. And let's take a look at the outcome, or even an event if it's a compound outcome. And we'll see what the probability of that is. So let's take a look at the possible outcomes here. When we toss 2 coins, we could either have 0 heads, 1 heads, or 2 heads. Now, when we did this, we had four possible outcomes here. All right, they want to look at getting exactly one head. So that's this situation right here. Well, we did these probabilities before. The probability of 0 heads was 25% or 1/4. The probability of 1 heads, if you look, here I've got HT and TH both satisfy this, and that's a total of 2 out of 4 of these, which is 50%. And then finally, 2 heads, we see that it's over here, 1 possibility out of a total of 4. So once again, that's 25%. And I've taken care of all the possibilities because this does add up to 100%. For part B, getting a 3 when you roll a fair 6-sided die. So let's see here. When you roll a fair 6-sided die, getting a 3, very simple. Just 1 out of 6 for all of those things. Our next topic involves playing cards. And since I'm not allowed to assume that everybody knows what cards look like, here's a deck of 52 cards. And unless I say other words, we're going to be dealing with a standard deck of 52 cards. That means we're not going to have any jokers in it. Those are extra. Toss those out. What you have left are 52 cards, and here they are. So let's do a few things and get some notation out of the way. These 12 cards off to the left, they are referred to as face cards. And then these guys down here are called aces. If you'll notice, we have various colors for all these things. Let's see, we have this here. The first row are called hearts. The second row are called diamonds. Try to fit them in here. The next one are called clubs. Those are easy. Sorry, I made a mistake. They're called spades. And then the last one, they're referred to as clubs. So each of those are called suits. And notice each row here, this is the suit known as hearts, has 13 cards. The ace they place at the beginning because in some games the ace can take the value of 1. In other games, the ace can take the value of 11. In all gambling games, usually, I don't want to say all because there could be some ones that contradict this, but in the gambling games that I know, at least in poker, for instance, the numerical value of king, queen, and jack are all 10, the same as this card. However, that doesn't mean they're the same power. This 10 here is less powerful than a jack, so in a standoff, the jack will win that battle. Likewise, the jack is weaker than the queen, and the queen is weaker than the king. And the one that beats all of them is the ace. So when you need to use the ace at the end after the king, you assign it a value of 11. All right, so let's keep that in mind. We have 52 cards. Four suits. That's 13 in each suit. Let's draw one card at random from a deck of 52. What is the probability the card is? So there'll be several parts here. A spade, red, an odd number, an ace, a red face card. So we'll start with the first one, a spade. Those are easy because the spades is one row here. There's a total of 13 of these cards out of a total of 52. So this one's really easy. It's just 13 out of 52. Now red, what's the probability of getting red? Well, you'll notice that rows 1 and 2 are all red. Since each row has 13 cards, I have 13 plus 13, which is 26. Or another way to look at it, that's exactly half the number that are in there. So we have 26 out of 52 for that. Now next, an odd number. Now here, when we're talking about odd number, the only cards that have numbers are the ones that go from 10 down to 2. The face cards don't have numbers, and neither do the aces. So we are going to count. I mean, they don't have a number written on them, so I'm talking about these numbers here. So let's count the odd numbers that are in one suit. So I'm going to do it on the first row. I've got 1, there's a 3 there, a 5, a 7, and a 9. So I had 3, 5, 7, 9. There's a total of 4 of them. And if I take 4 times 4, I have a total of 16. So I have 16 odd cards out of a total of 52. An ace, we have 1, 2, 3, 4 aces. And last but not least, a red-faced card. So if you take a look at here, here's the red face cards. There's a total of 6 of them out of 52. All right, so you pick somebody at random. What's the probability that their birth date happens to fall in July? So the probability of it falling in July, well, if we're talking about days of the year, there's a total of 365 days of the year. How many of them are in July? Well, there's 31 of them. So that's all there is to this problem. Next topic is relative frequency. So we're told that 4 times over the last 2,000 years, a certain river has crested to a high point. The relative frequency method is using the past probabilities or the past occurrences to use for future purposes. So, for example, we've had 4 floods in 2,000 years. So if you want, that's 1 flood for every 500 years. So this is the probability I'm going to use going forward. So that's what relative frequency means. That means the chances of this happening in the next year are exactly the same as they have been. So what is the probability that the river will crest above this flood level next year? Well, it's exactly 1 out of 500. We're using the past data to predict the future. Chet is an 85% free throw shooter. That means he makes 85% of his free throws. So if you want to think of it another way, you could probably say if he's up to the line to shoot free throws, out of every 100 shots he takes, he makes 85 of them. So we'll use that for the next thing. Suppose then that when he goes to shoot, so if he's fouled, is probability of making a free throw is also 85%. The next topic is an important one in statistics and probability called not. So not A, when I write this, A means that event A does not occur. So think about this. For any possible event, either it's going to happen or it won't. So since A either happens or it don't, we have the probability of A plus the probability of not A is equal to 100%, or 1. So if I want a formula for the probability of not A, I'll just simply subtract the probability of A off of both sides, and we'll get the probability of not A equals 1 minus the probability of A. So as an example, roll a 6-sided die. What is the probability of not getting a 3? So we'll use the probability of not 3 equals 1 minus the probability of 3. So here we have 1 minus, we know the probability of getting a number is equal to 1/6. So when you do this subtraction, 1 minus 1/6 is equal to 5/6. What is the probability of not getting a sum of 2 when 2 dice are rolled? All right, what I'm going to do is track all possible outcomes when we toss 2 dice and we add up the dots that appear. For example, the lowest possible score I could get is a 2. That's where both of the dice are 1 and 1. Now if I move on, if I throw the 2 dice and get a 3, the only ways I could have had that happen was the first dice be a 1 and the second dice a 2, or the first die a 2 and the second die a 1. Moving on to 4. I can get that by doing 1, 3, 2, 2, or 3, 1. Moving on, 5. I go 1, 4, 2, 3, 3, 2, 4, 1. 6. I can do 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. 7. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. 8. Now we have to start a little bit differently. Since these 6-sided dice, remember if I don't say anything, they're 6-sided, the numbers only go from 1 to 6. So I can't put 1, 7 here. I instead have to start at 2, 6, 3, 5, 4, 4, 5, 3, 6, 2. 9, 3, 6, 4, 5, 5, 4, 6, 3. 10, 4, 6, 5, 5, 6, 4. 11, 5, 6, and 6, 5. 12, 6, and 6. So now I have a question about some of these problems here. What is the probability of not getting a 2? So what we want is the probability of not 2, and that equals 1 minus the probability that it equals 2. Well, the probability that it equals 2, as you can see for the event that is called 2, there's only one outcome listed. So that's 1 out of 36. And then you can combine this to be 35 out of 36. Next topic is probability distributions. Toss 3 coins. Let me do sort of the way we can do it. Let's put an outcome here. And then we could put its probability. So let's take a look at some of the outcomes here. We have H, H, H. Then we had H, H, T, H, T, H, T, H, H. And then we had H, T, 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 H, T, 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 H, and then finally T, T, T. Each of these were equally likely with a probability of 1/8. And of course, check this out to make sure it adds up to 8 out of 8, and it does. That's one way to do it. A way that you'll probably see more often is this following way. What we'll call it over here is called the event. And we could take a look at the number of heads. So when you toss 3 coins, we either have 1 heads, or 0 heads, 1 heads, or 2 heads. And let's get the probability associated with each of those. So let's look at the probability of no heads. That would be all the way down here where we have 3 tails. And notice its probability is 1/8. Now 1 head, we have to look through here for all the situations where there's only 1 heads. There's 1 there, there, and there. So all of these, 1H. So that's a total of 3 out of 8. And then, oh wait, I can also have 3 heads. Sorry, made a mistake. Then 2 heads, how many of those do we have? 1, 2, 3 out of 8. And finally, 3 heads is only 1 out of 8. Notice that I've added it up to 8 out of 8, so it checks out. All right, here's a question involving 2 dice, and I have all the 36 outcomes listed here. So what I want to do is make a probability distribution based on this. So what you could do is, since they're asking for the most probable sum, which by the way, you should be able to see that the most probable sum here is 7, because the probability it happens is 6 out of 36, which is bigger than for any other number. So if we want to put the sum, let me make my table up like this. So I'll have sum, and notice the sums can go anywhere from 2 up to 12. So let me do that. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let me put their individual probabilities. Starting with 2, we only have 1 out of 36. So I'll put the probability over here. And then with 3, we have 2 out of 36. And then 4, 3 out of 36. Well, you see how this is going. The next one will be 4 out of 36, 5 out of 36, 6 out of 36. But that's when it got to its highest point. So by the time I got 6 out of 36, that means I've done that column there. And now we're going to start counting down 5, 4, 3, 2, 1. So we'll have 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. Check to make sure it adds up. It looks like I have 3 plus 3 is 6, 10, 15, 21, 36. Checks out. Now, so this right here is exactly what I'm looking for here. This is our probability distribution. It lists all the possible outcomes combined with their probabilities. Our next topic is odds. And let me illustrate this with an example. If you toss one die, a 6-sided one that is, and bet on 3, then 1, 2, 4, 5, and 6 are all outcomes. They're all possible outcomes. Against your bet. So with that in mind, here's how we set up odds. And the way we write it, you've got to be careful with this. So let's say odds of 3 coming up. So what we look at are all the ways that are good for it. That means if we bet on 3, then obviously I want the number 3 to come up. So there is one number that I'm interested in having, and that's 1. One number that I'm interested in having, and that's the number 3. However, the other 5 numbers I don't want, so they're kind of like against me. So that's like 5. So the way you do it is this. You have odds in favor of some event E. That will be the number in favor divided by the number not in favor. I don't know how much that formula is going to help you. This is probably a better example to illustrate that. But there is a second case here, a second formulation that you can do. I could say, what's the probability of a 3? And divided by the probability of not 3. So that would be one way to do it. So the probability, because up here, well, we'll see as things shake out. The probability of getting a 3 when you roll a die is 1 out of 6. The probability of not getting a 3 is 5 out of 6. And you might remember from your old algebra days that you work this by flipping the bottom fraction. I can simplify a little and I get 1 out of 5, just like what we were doing before. Note the book we'll use 1 to 5 instead. So the general formula of this odds in favor of an event E look like the following. The probability that E occurs divided by the probability of not E. Or if you don't like that formula, or that version of it, you can change the denominator to 1 minus the probability of E. And that way all you have to work with the whole time is the probability of E. Our next example, what are the odds for getting 2 heads when tossing 2 coins together? Well, let me list all the possible outcomes. When we tossed 2 coins together, they were like this. So the odds for getting 2 heads, so odds for 2 heads, that equals the probability of 2H over 1 minus the probability of 2H. So if we look at 2 heads, I've only got one situation there. And that's down below. I'll have 1 minus 1/4. 1/4 divided by 3/4. Remember to flip the second fraction. 1/3. Or 1 to 3. Here we have the odds are given as 7 to 5. If you bet $10 and Blue Moon wins, how much will you gain? Well, your winnings, here's how much you'll win. You'll get your $10 and they'll multiply it by 7 divided by 2. I think you'll find that that's $35. That's not all. You get your own money back. So there's another 10. So this is a total of $45 you'll receive after your horse wins.